Hello everyone, my name is Conache. I'm from TU Munich, and today I'm going to talk about the joint work with Markus Heidenreich, Franz Merkel, and Silke Rolles, based on a preprint available on arXiv at the link that you see here at the bottom of the page. Our work relates to a nice application of the duality between two models in statistical physics, namely a discrete Gaussian model with pinning at 0 and the lattice Coulomb gas, where we prove a spontaneous breaking of symmetry in the former model, and then using the duality between the two models, obtain information about the asymptotic behavior of the variance of voltages in the latter one. To see this, let's first introduce the models that we're working with. So first, the discrete Gaussian model with pinning at 0. Let me mention that we will be working with finite two-dimensional boxes lambda containing the point 0, with periodic boundary conditions. Our configuration space will then be the set omega lambda of all integer valued configurations, which are 0 at 0. The quadratic interaction in our model will be described by the local Hamiltonian h lambda x, which can be written also in terms of the discrete Laplacian, as you can see in the second equality. The partition sum of the model at positive inverse temperature beta is given by z lambda beta, which is equal to the sum over all configurations of the Boltzmann factors e to the minus beta h lambda of x. The corresponding finite volume Gibbs measure is then defined also in the standard way, as you can see here. The second model is the lattice Coulomb gas, and we will show via an application of the Poisson summation formula that it is indeed a dual of the previous model. Its configuration space will be omega star lambda, and this is defined as an intersection between the lattice 2 pi z to the power lambda with the set of real valued configurations whose sum of entries is equal to 0. This set k lambda can be thought of as the dual to the space of real valued configurations which are pinned in 0. The interaction in this model will be described by the Green's function matrix G, whose entries Gij are defined, as you see here, as this limit. Here in this equation, Pi is the law of a simple random walk on lambda xt, which starts in the point I. The partition sum of the model at inverse temperature beta star, positive, is given by z star lambda beta star, again as the sum over all configurations of the Boltzmann factor e to the minus beta star, 1 over 4, k transposed times the Green's function matrix G times k. Again, we have the corresponding finite volume Gibbs measure defined in the standard way. To see that the two models are indeed dual to each other, apply the Poisson summation formula to this function, exponential of minus x transposed times a times x, where the matrix A is given by minus beta times the discrete Laplacian, where we ignore here the 0 entries. The duality equation between the two models is given here and relates the two partition functions as follows. The partition function of the discrete Gaussian model, z lambda beta, is equal to z star lambda beta star times a factor depending on the inverse temperature beta and on the volume that we're working with. Also, the inverse temperatures of the two models are connected by a duality relation, namely beta star is equal to 1 over 4 beta. As I mentioned before, we will be proving a spontaneous breaking of symmetry in the discrete Gaussian model. So we will be working in the low temperature regime, namely beta going to infinity. And in the lattice Coulomb gas, since the two inverse temperatures are inverse proportional to each other, we will be in the high temperature regime, namely beta star going to 0. The main result is the following, states that for the observable Uij, defined as the sum over all sides in the lattice, in the box lambda, of the difference GIL minus GJL times the value of the configuration of the Coulomb gas at site L, which is nothing else but the energy cost for transporting a unit test charge between I and J, or in other words, the voltage between I and J in this lattice Coulomb gas. We will prove that its variance asymptotically behaves like some positive constant times 1 over beta star times the logarithm of the distance between I and J. In the as I mentioned before, high temperature regime, when we take the thermodynamic limit and then the limit of the distance between I and J going to infinity. This asymptotical behavior follows from the following main result. For all square boxes containing 0 and which have length greater or equal than 4 with periodic boundary conditions, and for all points in such a box, and all inverse temperatures beta star low enough, namely less or equal than 1 over 12, one has that the variance of the voltage between I and J takes values in this interval minus 4 over beta star squared, some constant depending also on beta star, plus 4 over beta star GII minus GIJ, and 4 over beta star GII minus GIJ. And if we look here at this interval, we can prove actually that this constant that we get over beta star squared will be converging to 0 as beta star converges to 0. So basically what we get as a consequence of this theorem is that the variance of the voltage between I and J asymptotically behaves as 4 over beta star GII minus GIJ as beta star goes to 0. And now taking the double limit, first the thermodynamic limit and then the distance between I and J going to infinity, we can see that what the behavior of the Green's function is, it's nothing else but a constant times the logarithm of the distance between I and J. So that's how we prove our main result. For the proof of the theorem, we will be showing that we have a spontaneous breaking of symmetry in the discrete Gaussian model, and we will use the duality between the two models. In order to prove the spontaneous breaking of symmetry in the first model, we will need to perform a Peierls argument. Now, while Peierls arguments on planar domains are classical, the treatment of non-zero homologies due to the periodic boundary conditions are less common. And let me show you now a picture of a possible spin and contour configuration in the discrete Gaussian model. And let's notice that also we have here a finite box. We have an integer valued configuration, and we will need to define contours that we will work with to perform the Peierls argument. Now, we will draw arrows between neighboring sides where the values of the configuration differ. So for example, take this point taking value where the configuration has value -1, and this neighboring point where the configuration takes value 1. And we will draw arrows on the edge of the dual lattice intersecting the edge ij here. And the number of arrows will be given by the difference in the values of the configurations at these two sides. So here we have 1 minus -1. We have 2 arrows. Their orientation will always be such that the larger value is on the left of the arrow. In doing this, we obtain 2 types of contours because of the periodic boundary conditions. The first one is the typical one, namely the closed cycles, like you see here, the green one, the closed cycle. And the second type is given by winding pairs of contours around the torus, like you see here in the red contour. So you have periodic boundary conditions, and these go on and on and on. Good. Now, by performing the Peierls argument, we obtain the following result. We obtain that for beta large enough and uniformly in the volume and in the points that we choose in beta, the probability that the values of a configuration at points I and j are different by more than some given natural number k, this probability is exponentially small. The function phi beta is a function of the inverse temperature beta and is exponentially small as beta goes to infinity, and in particular for beta greater or equal to log of 6, we get that this phi of beta is definitely less than 1. So this quantity here will be converging to 0 as k goes to infinity. Using this Peierls argument and the result of this proposition, we can prove then the spontaneous breaking of symmetry in the discrete Gaussian model with pinning. Namely, if we consider the observable given by the square of the difference between the values of a configuration at sites I and j, we obtain that for beta large enough, namely greater or equal than 3, one has that uniformly in the volume and uniformly in how we choose the points, the sites in the volume, the expectation of this observable is less or equal than some constant depending on the inverse temperature of beta, which is asymptotically equivalent to 2 times phi of beta, and this phi of beta was, we know, converging to 0 as beta converged to 0. So this proves the spontaneous breaking of symmetry in this model, and using this result and the duality of the two models, we can then prove the asymptotic behavior that I mentioned before. Okay, this was everything that I wanted to share with you. Thank you for viewing my talk, and I would be very happy to answer your questions during the live session, which will be taking place at the end of September. So thank you. Goodbye.